Toricelli's theorem describes how fluid flows out of an orifice under the influence of gravity. It states that the speed of the exiting fluid depends on the height of the fluid above the opening, linking fluid motion to gravitational potential energy. This experiment explores the relationship between fluid height and flow rate, allowing us to observe how the theorem applies in real-world conditions. By measuring and analyzing the fluid's behavior, we gain a deeper understanding of the principles governing fluid dynamics and energy conservation. The objective: verify Toricelli's relationship by comparing measured and theoretical value of velocity. The scope: the experiment was repeated with orifice heights of 36.65 cm, 56.45 cm, and 76.15 cm. It was tested with 5 different volumes, which is 2 liter, 1.75 liter, 1.5 liter, 1.25 liter, and 1 liter.
For the theory, Toricelli's law states that the square root of the vertical h between the liquid surface and the opening center and the square root of twice the acceleration due to gravity, g, are both proportional to the speed v of a liquid flowing beneath the force of gravity out of a tank opening. The formula is v equal to x, the square root of g over 2y. This is the Toricelli's experiment, but during the experiment we don't use mercury, we use water. This is just for the theory how Toricelli found this equation and give the theory. In the early 1600, Galileo thought a suction pump worked because a vacuum inside the pump pulled water out. After he died, Evangelista Toricelli, an Italian scientist, had a new idea. He said air has weight, and the pressure of the atmosphere pushes the water into the pump when it's empty. In an experiment, some mercury drained from a glass tube into a dish. Toricelli explained that the mercury stopped their draining when the weight of the mercury in the tube balanced the pressure of the air pushing on the liquid outside. Toricelli also noticed that the height of the mercury column changed with the weather because the air pressure changes. He invented the barometer, a tool to measure air pressure. Standard air pressure is 1 atm equal to 760 mmHg. At sea level on a sunny day, the weight of a 760 mm column of mercury balances the pressure of the air. This is why we say air pressure equals 60 mmHg. This is how we derive the Toricelli's theorem equation. Assuming that the fluid is incompressible, Bernoulli's principle states that v square over 2 plus gh plus p over rho equal to constant, where v is speed of liquid, g denotes as gravitational acceleration, h is the liquid's height over reference point, rho is density, and P is equal to atmospheric pressure at the top of the container. V is considered as zero because the liquid surface drops in height slowly compared to the speed at which liquid leaves the tank. H is zero and P is atmospheric pressure at opening H equal to 0.
This is the experimental setup for this experiment. First, we have clay marker, and then we have cylindrical cylinder, and then we have measuring tape and stopwatch.
Step 1. The path was placed on the floor and a measuring tape was stretched along it. A rack with an adjustable platform was placed at the zero end of the tape. Step 2. A cylinder with a hole was placed on the platform, so the center of the hole was 36.65 cm from the floor. The cylinder was moved on the platform so that the hole aligned with the measuring tape. The hole was covered with clay to prevent water from leaking out. Step 3. 2 liters of water were poured into the cylinder. The starting water level was measured and recorded. Step 4. The clay covering the hole was removed, and the stopwatch was started as soon as the water began to flow. The first spot where the water landed on the path was marked with clay and its position was measured. Step 5. This marked the maximum distance the water traveled. The stopwatch stopped when the water stopped flowing and the time was recorded. Step 6. Steps 3 to 5 were repeated twice to get an average result. Then the process was repeated with 1.75 liter, 1.5 liter, 1.25 liter and 1 liter of water. Finally, the process was repeated with the hole at heights of 56.45 cm and 76.15 cm.
Safety procedure. First, any unnecessary items were removed from the workspace to prevent accidents, and all devices near electrical equipment were adequately protected from water exposure. Second, the water container was stabilized and placed on a flat surface to prevent tipping. Third, absorbent materials or towel were kept nearby to promptly clean up any water spills, reducing slip hazard.
Y equal to 0.3665 for table 1. Y equal to 0.5645 meter for table 2. This is the result for y equal to 0.7615 for table 3.
Discussion. Explain your selection on dependent, independent, and constant variable.